Let's get started. So yeah, my name is Michael Pradel, and I'm talking a bit about one of the four focus areas of the unit, which is about natural and programming language processing. So here are the pictures of those people who are definitely associated with this area. If we are getting more members, there will probably be more people, but as you have already heard a little bit about them, I will not go through all the names now. What I will focus on in the next 20-25 minutes is the second part of this topic area, which is about programming language processing, which for kind of average ML people might be a bit of news because programming languages are not among the typical data that most people look at. But I hope I'll be able to convince you that it's actually very interesting kind of data to look at. So to motivate all of this a little bit, so when we talk about programming languages, then of course our key users are software developers, and the reason why we would like to help them is because software developers really need good tools. So I assume many people in this room have already developed some software, so I'm sure you know about this. And the reason why tools are so essential is that they are really at the core of what makes us humans, right? So our ability to develop tools has been really important for the way this planet has evolved so far. So we started with very simple tools to change our environment, and then had much larger tools to change our environment. And now, well, the world is eaten up by software, so software development tools are really important these days. And I'm sure many of you have already used many of them, like compilers or maybe bug detection tools, or maybe some code completion system. Now the question is how to create these software development tools, and the traditional answer until a couple of years ago has basically been traditional program analysis. And this is also an exciting topic, so I've done quite a lot of work in that area, so I don't want to say this is a bad way of doing this, but I'll show you another way that is also very interesting. So what this traditional program analysis is basically doing is to reason about source code or maybe executions of source code through precise and logical reasoning. And typically such an analysis is manually crafted over a couple of years of work. So maybe someone does a PhD on a particular kind of analysis, and then after n years there is an analysis that eventually works. But of course, in order to make it work, you typically need a lot of heuristics, because almost all interesting program analysis problems actually turn out to be undecidable. So to get a practical tool, you need to have some heuristics. Another interesting property of the traditional program analyses is that they are typically challenged by large code bases. So if there's more code, that's bad news, because they usually don't scale that well, which is something we, of course, would like to change. And the alternative that I'm going to talk about here is what I call neural software analysis. So it's basically training neural networks to do program analysis. And this kind of analysis differs quite a bit from the traditional kind of analysis that I've been talking about before. So one difference is that instead of needing years of manual work, you can, at least in principle, automatically learn such an analysis within a few hours or days, depending on your hardware and the kind of task we're talking about. Instead of precise and logical reasoning, this kind of analysis is based on data-driven prediction, as basically all the time in machine learning. Of course, there will also be a lot of heuristics, but we do not have to hard-code these heuristics, but they are learned from data. And I think the maybe best property of all of this is that large code bases are not a problem, but actually part of the solution. Because if there's more code or more executions of code or more data around programs, this will be used to the benefit of a neural software analysis. So at a very high level, the big picture looks like this. So all of this is based on this insight that there is a lot of data about software development, not only code, but also other data like execution traces, documentation, bug reports, and a lot more. And the basic idea is to feed this kind of data, or some of it at least, into a machine learning model, which then gives you some kind of predictive tool, and I'll become more precise in a few seconds. But once you have this predictive tool, then you can give it new code or new executions, and it will hopefully be able to provide some prediction that is useful for developers. So this overall idea hasn't been around for so long. So if you look at this overall field of neural software analysis and just try to look at how many papers there are per year, then you basically see that until like 5 years ago or so, there was almost nothing. And around 2015, 16, the first few papers showed up and showed that, hey, if you apply neural models to software, it actually works. And by now, there really is a lot of research in this field. Here, just give a few of the tasks that people have been looking at. So it includes things like code summarization. So you have a piece of source code and would like to summarize it into a short natural language description, or maybe type prediction, where you have code that doesn't have type annotations, but you would like to add these type annotations, or bug detection, so finding out that some piece of code is wrong, program repair, so once you know the bugs, people try to automatically fix them, and of course code completion, which is probably the kind of application that most of you may have already used that fits this theme of neural software analysis. So talking about this code completion, let me just mention two actually already approaches that are already in practical use, namely Tab9 and Copilot. And probably some of you have already used at least one of them. So what both basically do is to sit in your IDE and help you program by predicting some code. And under the hood, there's a big neural model that has been trained on a lot of code and basically knows how to complete code. So after this little introduction into the field as a whole, let me say what I actually want to talk about in this talk here. So I will give you two relatively recent examples of neural software analyses that we've been working on. One called Nailin is about finding name-value inconsistencies, and we'll see in a second what that is. And the other one called Typewriter is about type prediction. So the problem that you have a lot of code, but sometimes the code is missing type annotations. And then at the end, I will talk a little bit about one of the big open challenges in this field, which is about understanding what these models of code are actually doing so that we can better improve them in the future. So let me start with the first topic, the name-value inconsistencies. And as a little bit of motivation, I've here just a tiny bit of Python code. So since most of you work on machine learning, I'm sure you've written some Python code. So I just leave this here for a few seconds, and maybe someone could spot what might be wrong with this code. You don't see the iris in the third line? Yeah, that's not a problem I'm hitting at. Of course, this is incomplete code, so there's stuff missing, but there's also something that is wrong, yeah. Exactly, that's exactly the problem. So the train size that is computed here will be a floating point number. So it's 100, in the execution, it's 135.0. And then if this is used in the third line to slice this data array or whatever it is, this is not going to work. So this will actually break and crash the program. Here's a second example. In this example, nothing is really fundamentally wrong in the sense of the code misbehaves. But there's a pretty misleading name because someone is basically checking whether some file exists and then stores the result into a variable called file, which is a pretty strange name for a Boolean value. So usually for the name file, you would expect maybe a file name or maybe a file pointer or something like this, but probably not a Boolean. And what these two examples have in common is that there is a name and a value, and both are inconsistent with each other. And our goal in the Nailin project is to essentially find these kinds of name-value inconsistencies, and we train a neural model to do this. Now, if you look at this goal, there are basically three fundamental challenges that we need to address, which a traditional program analysis is not really able to address. The first challenge is to understand the meaning of names. So in order to know that a name and a value are inconsistent, we somehow need to have an understanding of names. As humans, we're pretty good at this. You look at the code, and as you've seen, people are able to spot what's wrong, but a traditional program analysis just cannot do this. The second challenge is about understanding the meaning of values. So once we know what the names mean, we need to look at the meaning of the values that are associated with the names. And then finally, of course, we need to pinpoint unusual combinations of names and values, and we want to do this in a precise way so that if you report such an inconsistency to a developer, chances are high that this is actually a problem. So let me show you how we do this, and I won't go into all the glory details, but just give you an overview of how this approach works. So as many of the approaches in this area, there is a training phase and a prediction phase. the input to both of those are executable programs. So in contrast to a lot of other work in this field, we're not just looking at the code, but we're actually executing the code. And by doing this, we basically perform a dynamic analysis of assignments. So basically, locations in the code where some value is bound to some name. And this gives us a lot of examples of supposedly good combinations of names and values. And then in order to train a classifier that distinguishes good from bad combinations, we also have a generator of negative examples, which I'll not explain here in detail, but essentially what we get at the end is two kinds of examples, consistent examples and inconsistent examples. And then we can train a neural model that is essentially a binary classifier telling us whether an example is consistent or inconsistent. And then once it is trained in the prediction phase, you can query this neural model with code or executions of code that the model has not seen before. And then hopefully it's going to report some interesting name-value inconsistencies. To make this a little bit more precise, let me show you some of the data that we are gathering here and that we are eventually providing to the model. So what you see here are 5 examples of a variable name in the first column, and then the value represented as a string, just what you would get in Python if you just say str of some value. And then we also record the type and if there is the length and the shape of a value. And all this information basically helps the model at the end to understand what the meaning of this value might be. Once we have this data, we feed it into a neural model, which is shown here. So we have these 5 pieces of information, the name, the value, the type, the length of the value, and the shape of the value, and then encode each of them using some suitable kind of neural module. For example, we embed names using a pre-trained fast text embedding, or we represent the string representations of values by feeding them into a GRU and also into a CNN. And then all of this is concatenated into one vector that basically summarizes what we know about a name and a value. Then we have a few feed-forward layers, and at the end, the model predicts the probability that this combination of name and value is inconsistent. And during training, of course, we provide labels for that, and then later on, we use this to find inconsistent combinations of names and values. So after this little overview of the approach, let me talk a little bit about some of the results we got. So we applied this to almost 1 million name-value pairs that we got from executing a lot of Jupyter notebooks. The reason for choosing Jupyter notebooks is simply because they are more or less self-contained and can be executed without too much additional work. Once we train this model, we get a classifier that has an F1 score of 89%, so it's pretty accurate at distinguishing the consistent from the inconsistent examples. We also performed a user study where we basically show that if our tool, Nailin, points out some inconsistency, then this strongly correlates with what developers perceive as hard to understand names. And finally, we also compare Nailin to existing static checkers, so basically the tools that software developers would use nowadays, and we find that Nailin complements these existing static checkers. Let me show you a few examples of inconsistencies that we found. So we manually inspected some of them, and here you see the result of 30 manually inspected warnings that our tool points out. So we find that most of them, 21, are actually misleading names. So nothing is really wrong in the code, but it's a name that if you would like to maintain this code, should probably be changed. One example is here, where some variable called name initially stores something that is actually a name, and then later on stores a floating point value, which is probably not what you should do. Another kind of problem is actually incorrect values, so places in the code where there's a bug because someone has assigned a value to a name and it's just plain wrong. One example here is this variable called prop, which supposedly stands for probability, and the value that this variable gets at runtime is a string corporate because of some bug in the code. And then if later on this prop is compared to 1/2, the code will actually crash because you can't compare a string and a floating point value in Python. And finally, because that's a trained model and they are never perfect, there are also some false positives, like this one, where the variable name dwarf supposedly means that there is a file, so the capital F probably means file, but the model somehow didn't really understand this abbreviation, but since it is probably clear from the context, we classified this as a false positive. Good, so now you might say, well, if you had a type checker and a language with types, wouldn't we find all these problems? And the short answer is yes, at least for some of them. But there's a big but, and that is that there is a lot of code that just doesn't have any type annotations. So if you think about all the Python code that people are writing, some of it comes with type annotations, but a lot of it doesn't. And this is a problem for maintenance, because if you have a lot of Python code, and maybe if you have a lot of Python code in a company, it's really a nightmare to maintain this code. To illustrate this, let me show you an example. So this is, again, a piece of Python code, 2 functions. It doesn't really matter what exactly the code is doing, but what we would like to do with this code is to automatically predict the types of the function. So we would like to know what are the argument types, in this case the type of this color parameter, and what are the return types of these functions. And now in order to do this, we extract different kinds of information from code, and then give this information into a neural model, which we then train to predict the likely type of a particular code element. So in particular, we here look at the code itself, represented as a sequence of code tokens, which we feed through a recurrent neural network. We also look at natural language information that is in the code, in particular identifier names and comments associated with a function, which are also embedded and then summarized by a recurrent neural network. And we also look at the types that are already imported in a file, because that usually gives a hint about which types are relevant. And then at the end, the model predicts what we call a type vector, which is basically a probability distribution over a fixed set of types, and tells us how likely the types that we have are for this particular code element. So what you get out of this, and now I'm back at the example that you already saw, is a list of ranked predictions for every missing type annotation. So for example, a model might tell us that this color parameter most likely is an int, or maybe second most likely is a string, or maybe it's a bool. And similar for the return types of the function, so we always get this list of likely types that you could add here. Now the problem is, because the models are imperfect, if you do this for a larger file, or maybe for an entire project, and you just take the topmost prediction everywhere, you will actually introduce type errors. So if you do this and take the topmost prediction here and add them to the code and then run a type checker for Python, it will basically give you errors and tell you, well, this is not the right set of type annotations. And if you think about this, this is actually an interesting search problem, because you have different places where you want to add type annotations, and for each of them we have a list of predictions. So what we do now is to look at this as a search problem and basically search for a consistent set of types that we can add to a particular file or to a particular project, so that everything at the end is type correct and will type check. So to do this, you basically take the top k predictions for each location in the code where the type is missing, and then filter those predictions by running a gradual type checker, for example, MyPy or Pya for Python. And then in order to be efficient, and we don't need to try out all possible combinations because there are just too many, we have a feedback-directed search that basically tries to minimize the number of type errors, and at the end we only suggest types if there are 0 type errors, while maximizing the number of type annotations. So we want to add as many annotations as we can without at the end getting type incorrect code. So getting back to the example, so this was the code. These were the predictions that we get, and I told you that if you just take the topmost predictions here, then this is wrong. But then after running the search, which basically goes down these different lists of predictions and tries to combine them in a clever way based on feedback, we at the end find the correct predictions, which in this case would be the second for the color parameter and the second for the return type of this find match function. And it turns out that this combination of types at the end gives you a type correct program. Let me here also talk a little bit about the results we got. So this was some work that was done during a sabbatical I did at Facebook. So one of the code sets or code bases we applied this to was all the Python code at Facebook. In addition, we also ran it on 6 million lines of open source code. And the results we get yeah, you can see here. So if you just look at the neural model, it's relatively accurate. So it gets an 80% F1 score within the top 5 predictions for individual type annotations. But now 80% is not perfect. So if you would add all of them, you would introduce a lot of type errors. But if you now combine the neural model with this search, then the overall approach is able to correctly annotate 70% of all the annotations in a given file. So it can actually take unannotated Python code and add the majority of all the annotations that you would like to see there. And interestingly, despite the fact that this is not based on logical precise reasoning, it actually in practice subsumes a traditional static type inference algorithm. So if you just compare this to existing static type inference algorithms, then basically this typewriter approach finds practically all the types that the type inference can also produce. So let's take a step back now and reason a little bit about why all of this works. So one reason is that developers are actually pretty reasonable people, and they tend to use meaningful names, which means if we learn from these names, we can actually get lots of insights into the code. Another reason why this whole area is so successful is because source code turns out to be very repetitive. So if you just look at code written by completely independent people, it turns out that they tend to write very similar code oftentimes, which is good for learning because then there are patterns you can pick up. Of course, we also benefit from the fact that many programs are available as training data. And finally, this combination of probabilistic models and natural language is really very successful, as the whole NLP community has also figured out. So these were the good sides. Let me now use the final 3 or so minutes to talk a little bit about some of the challenges that we are facing in this field. And one of them, which I think is shared also with other application areas of machine learning, is that it's sometimes really hard to know what these models are actually doing. So working in this field sometimes feels a bit like being one of these medieval alchemists that try to put together different ingredients in order to eventually find gold, but they don't really understand what they are doing. And it sometimes feels a little bit like this to work in this field, and I'm sure people who work on other kinds of data may share this feeling. So we don't have the solution to this challenge, but as a very first step to better understand what these models of code are actually learning, we've been comparing humans and neural models that work on the same task, look at the same kind of code example, and then in order to compare them, we basically compare what parts of the code the humans or the models pay attention to. So for the humans, we've built an interface to capture attention. For the models, we use the built-in attention mechanism. And then we can compare the two, and that actually helps us better understand the differences between the humans and the models, and ultimately also to better understand what the models are really doing. I don't have time to go into all the details. There's a poster outside that Matteo will be happy to tell you more about, which is actually about this work. Just to give you a glimpse into the results. So here is the two attention maps on the top. That's the attention map that we get from humans trying to understand this code. And at the bottom, you have an attention map of a neural model trying to understand this code. And if you just visually look at it, the two attention maps look very different. So somehow the models are not really doing what the humans are doing. And we also looked a little bit closer, and just to highlight some of the findings. So one interesting finding is that the model spends quite a bit of attention on understanding the basic syntax of the code. So it looks at semicolons, curly braces, this kind of stuff. And humans completely ignore this because they see visually where a line ends and where a code block starts and ends. So arguably, you should probably feed more of the syntax information into a model so that the model doesn't have to waste its attention on that. Another interesting finding is that the model tends to ignore some of the tokens that developers find really important. And one example are strings. So the developers get a lot of information out of strings, whereas the models, at least the models we studied here, completely ignore the strings. So there's potential for improving models like this by teaching them to basically also reason about string literals that are in code. So looking at the time, maybe let me jump one slide ahead and almost reach the conclusion by looking a little bit into the future. So I've shown you this increase of work in this area, but of course I don't think that's the end. Actually, there's a lot more that people should do and will be doing. And three interesting directions of future work that I see are to make use of these general purpose language models that are really popular these days in NLP and also in the program analysis field, because they are really powerful, and I think the potential of them has not yet been explored. Another interesting direction we are working on is to combine neural and traditional program analysis. This typewriter approach, where we basically validate type predictions using a type checker, is one example. But yeah, there are many more ways of doing this, and I think that's a very fruitful direction. And finally, I think more work should be done on reasoning about execution, so not just about source code, but actually about executing the code, because that tends to give you more precise information about what's really going on in the program. And with this, I'm at the end of my talk, so thanks a lot for your attention, and I'll be happy to take questions.
So do we have students to maybe take the microphones? That would be great. Then I don't have to do all the running. Only one right. All right, are there any questions?
There are two here.
Thank you for the very interesting talk. I was wondering if there is a qualitative difference between training on Jupyter notebooks and, let's say, like library code or code bases at companies or whatever.
Mm-hmm. Yeah, that's a great question. The quality of the code plays a big role, and I think Jupyter notebooks, I mean, I don't want to offend anyone, but arguably are the worst quality code you can find, because many of these notebooks are just write-only, right? You write them, you explore something, and then you throw it away, and you never really aim at maintaining the code. Yeah, there was a trade-off in selecting the code we used for this work, and the reason for Jupyter notebooks was just that it's easy to execute them. But ideally, yeah, in future work that reasons about executions, we should look at like test suites of big open source projects and big libraries. Yeah, good point.
Thank you for the interesting talk. I would suppose, like in a real-world programming application in an editor, you could use the idle time for the combinatorial search. So I'm wondering, how much gain would you expect from more time for this combinatorial search?
So the combinatorial search is really too expensive to completely finish it. So even in the idle time, I mean, unless you want to wait for many months, it just doesn't work. The reason is that in a single file you may have, I don't know, 50 or so missing type annotations. Now for each of them you get some suggestions, and then it's an exponential complexity basically, because if you want to try out all of them, and then for each of them you would have to run the type checker, which may take a few seconds. So there's no chance you can really try this exhaustively, at least not on a larger code base. So if you have just like one slide of code, it works. But if you want to do this on, say, Facebook's code base, there's no way you can really do it.
It's all in the same spot.
It seems there's
very convenient.
A question cluster here. That's good.
So, in terms of the similar problem, is those predictions, like the type predictions, are they made independently in a way, or would there be a way to make them kind of correlated such that we can automatically see me rule out unlikely combinations?
Yeah. That's a great question. So in the piece of work I've been presenting here, they are made independently, but actually we know there are dependencies, right? So if one function returns something and that's used as a parameter into another function, then they should probably have a compatible type, or maybe even the same type. And yeah, it would be great to have a combined prediction there. That goes in this direction of combining traditional and neural analysis, because a traditional program analysis basically knows about these dependencies, and integrating that more closely, yeah, would make a lot of sense.
Thanks.
Any other questions? We still have time for maybe 2 very quick ones and 1 not so quick one. There's one.
So I have a quick question about this slide. Actually, it's related to this one. So in IDEs, there are a lot of tools for to help developers creating software. So can you quantify, like, roughly the percentage of these tools that are like machine learning or deep learning based, and the other ones that are still hard-coded, and what is like the area or chance of improvement in these ones?
Yeah. I think that depends a lot on what plugins you install in your IDE, basically. So I mean, I know that there are at least dozens of very popular plugins that people have been using, like Copilot or IntelliCode, that people are using. No percentages, I don't know. I mean, this field as a whole is still relatively young, so I think the majority of what is currently used in IDEs is still traditional program analysis, but the trend is clearly going toward also having neural, and I don't think it will completely replace the traditional techniques, but at least complement them in various ways.
All right. Well, thank you very much again for the interesting talk.